Yes, I have one or particularly two questions for Professor Krüger. So, thank you so much for your wonderful talk. So, the first question is like, is there any possibility that we can get the classical SIR model from your BZR graph model based on the kernel? Is there any functional form so that we can put it?
The classical SIR model is a special case. It's a limiting model of this classes which I presented here, right? So if the Erdős-Rényi graph structure gives you the classical SIR epidemics already with exponential distributed, so just the timing is, and so you still have to add like in this first passage percolation, the mean generation time, which is exponential in the usual case. This is somehow the standing things which gives you precisely then in the limiting case the differential equations for the SIR model.
Okay.
And
so,
if you do the SEIR model, so which the exposed group, it just has no structural impact on the graph is the same Erdős-Rényi graph, but it just the timing is now a gamma distribution instead of an exponential distribution. So that's what comes in here.
Yeah, thank you. And another question is regarding what does the household structure means? Is that only the size of the household, or is there any?
Yes, I looked at what I did here today it was only depending on the size of the house. It's true that there's still more fine structure inside the household because the age distribution in the household also matters. Now, most of the things I showed here, you can extend to age coupling. So if I really put a kernel now in where age coupling is, but the formulas get a little bit unhandy for a talk. I mean, right, they're getting already unhandy at some points even here. And it would be just, I think, you wouldn't gain now deeper insight putting these things in from a mathematical point of view. And it adds a little bit, it shifts a little bit, right? So especially Poland has this additional problem that we have a lot of 3-generation households, which transports, especially if you now have schools in, I didn't have the schools here, they're explicitly discussed, but if you have the schools in and they have a 3-generation household, it's not good for the elderly people. Germany is almost absent of 3-generation households. When the children go out, so in the time when the children are in, the elderly, the grandparents are never in the households. So it's really a very, very different thing, which is still an additional risk factor. So this can have also unfavorable age couplings in the household itself, but it's a little bit more complex now for working out. We haven't also done it in full details. In the simulation, we have it, of course, in.
Okay. Yeah. Thank you so much.
Mm-hmm. Other questions? Anybody?
I have a question. So that's a nice map of Germany, Poland with the regional differences in household size. And I wanted to know whether it tried to test the theory on regional values.
Yeah, I mean, we would very much interested in going more deeper in the resolution of these regional differences, because we have the regional structural differences via the household size. We actually have it for Poland, the household size distribution, the precise distribution, also the age correlation on 10 by 10 kilometers resolution, which is very, very high. You don't get in Germany, I mean, in Germany, you don't get it as high level because by privacy issues, I would say. You also maybe cannot use it. So the picture I showed you was, I think, 10 by 10 kilometers, which would be completely fine. And I would very much be interested in seeing, I mean, we have this method now, which somehow divides apart the cumulative effect of restrictions, what you did, and testing and contact tracing, and the structural impact coming from the local regional household things. And it would be naturally tempting to do now this on regions. right? Maybe on the Kreis or Gemeinde level, or in Poland on Gmina or Województwo level. It's just a matter of workforce. We don't have enough workforce now to go into the regional studies. We planned this since a year, but up to now we have refused to do so just because I don't have people which would do this. I would be very happy if we could put this, for instance, also as a project a little bit, even if we just do it regionally here in the local neighborhood, right? But here I really have a little bit, we have relatively good conceptual things what to do, but it needs then also be handcrafted a little bit, everything, right? It's not just automatically coming out, but it's planned, yes. Thank you.
I'll ask one. If I understood correctly, it looked to me like the individual-based model, the network model, allowed you to incorporate heterogeneities, the assumption of the BGR type networks, and the corresponding network theory allows you to translate that into aggregate quantities like R0, the household boost ratio, things like that. And then the actual statistical fitting comparison of the model results to the data happens at the level of the aggregated quantities. So you're looking at total number of infected and things like that.
Right.
So my question from a kind of empirical perspective is, how much does the actual structure of the real contact network, which you don't know necessarily, matter, and how much could that change things relative to what you're assuming in the theory?
Yeah, I mean, actually, I wanted to make a little bit to stress this point. It's to understand the impact of the real network structure. Not everything makes equal impact, right? And the ones, for instance, if you have large inheterogeneities in out degrees, but the target where the edges go is somehow very random, this has little impact, the heterogeneities. But correlations can quickly create subcommunities which have a different epidemic dynamics, right? So for instance, we made one correlation here, which is still related to the household. We looked for the situation when vaccine denials, or when this opinion somehow about vaccination is clustering in the household, right? Which is a relatively natural thing that families somehow have, maybe not 100%, but a majority opinion about vaccination. And if I'm children, somehow 16, 17 years old, of a very, very engaged mother in alternative medicine, I maybe have a problem in accepting vaccination because I was told that that's school medicine and not good, right? So this could be a likely scenario. And we looked a little bit at that, and that indeed creates a problem, but this is still easily to catch because it's in the household now clustered. What I'm not so sure about how much actually we have segregation in so the general rule is the following. If you have segregation in a network structure, so you have subnetworks which are loosely connected between each other, but maybe highly connected in each other. A lot of things can happen. You can have an overcritical epidemics in a subpopulation, which quickly goes through, and then it's over somehow. And the other one is just a little bit driven out. But we don't really know this non-local, because these are non-local features, right? So real kind of onion structure in the population. These are global network features, which you can't, it's very hard to reveal this from local structures. You really have to somehow search from the local network. Probably, yes. I think there is, especially in, if you have groups with different cultural background, for instance, right? So, which we have in Germany, not so much in Poland. It's much more homogeneous from social differentiation within the population. But usually groups with different cultural, educational background form somehow also clusters in their own, right? Because they are somehow, well, educationally less well, the education failed somehow here, or you have problems related to subpopulations which are very poor. Poor subpopulations still have the tendency not only that their friends are also poor, but they live also under very, very bad living conditions, in the sense very small sizes of the houses and they're living many familiar small houses, and then still a little bit isolated from the normal. So here you could have definitely epidemiological threats, right? Correlations could also appear, but this is essentially all unknown, that related to your attitude to COVID, right? If I'm an activist against COVID, right? So like this Querdenker or so, I like our Querdenkers, right? So the people who don't protect themselves are more likely to meet people which also don't protect themselves. That is a coupling, and this can create overcritical subnetworks within a large. It's still then, it's just a giant component. It's not as large, but it's still a giant component. You can get an overcritical epidemics. We have studied this a little bit. The problem is the data for the network is so poor. Yeah, that is really the problem. So I hope that many of the suspected heterogeneities of the networks don't have so much input. There's one thing where I can say a little bit more, and this is about, you might say, well, the reality is not locally trees. They look like you have triangles, right? And the physicists they're one of the first 20 years which studied really the local clustering things, number of triangles, friends of mine are friends, my friends. This has not so much effect, because it has effect. Every triangle, local cycles slow down the epidemics, because you quickly get an infected, which meets another infected, right? If I have a triangle, I have the possibility that I infect two people, and these two people also meet each other, because they are both of my friends, but they also know each other. And then one of the infections goes actually void, right? So potentially both could infect, but because they are friends and they are already infected, this is somehow a non-relevant infection. So local clustering structures usually slow down epidemics a little bit. But if you look really all what is known on this network stuff, it's still a little bit, it has still this tree structure, but the tree is a little bit fat. So it looks like maybe something like that. So you have to understand a little bit the process of network forming. Right, so if I take a triangle here and I put maybe another triangle here, and I put things like that, this is now an idealized thing, but you see immediately that this is still a tree structure, right? This triangle is neighbor to 3 triangles, and the branching number is actually 2. So every triangle generates 3. Also, the edges I have is 1, 2, 3, 4. Right, so you would expect that the reproduction number might be 3, but it's not. The branching number is 2, because 1 here infects essentially 2, right? That is the growth, how the network growth, it grows like 2 to the power of number of generations. And the reason why I think this is the more relevant structure comes from the following fact. If you look how the real social networks arise, I mean, we have the workplace, we have we have families, we have somehow some interest. And so let's put it that way. I mean, I have my sport club, I have my pub, and so on. And people, and here are the people, right? So we meet maybe at places where other people also go, where we work together. This is maybe the sport club I'm going, and this is the pub I'm going, the restaurant here, and then there's maybe still, well, I don't know. Anyway, people going and meeting at the same place have an enlarged and not longer depending on the size of the population probability to know each other and also to infect each other. So the induced structure, this is a bipartite graph. The induced, and here are not people, here are places, right? So certain things where we meet, where the social activity is going on. To generate now a network out of this, you do a projection. You give somehow everybody who meets here a likelihood to have this. And what we get here is a generalization of this structure. So I have maybe some cliques here or some denser graphs, and then maybe they are a little bit linked like that. But the overall thing is, after going a little bit further apart here, you have maybe little squares here. Rarely, sometimes you have a common edge, but sometimes you have. And then again, you have a triangle here. And things like random structures, which are highly connected, are glued together in a tree-like fashion. That is what is social networks usually looking like. Now, effectively, this is still a tree structure. It's a fat tree structure. The Bolle-Jansen's theory actually extends to this type of things, because instead of making edges, you can plant a little object like that. But they still will be connected in this way. There is still an overall tree structure. And otherwise you couldn't, yeah. And this is more difficult a little bit, the details, but I think it will not be really changed dramatically, the picture.
So basically, if the underlying contact network can be aggregated in some way to a tree structure.
And yes,
the theory applies.
So networks which are like in plant epidemics, where it's really, you have a parasite which jumps from a tree to the next tree. This is really different. Here, the spatial structure matters much more. And you have a cycle structure, which is, this is not tree-like, right? But I think everything which is human societies, I mean, all what we know, have this small diameter property. Small diameter means essentially that depending on the distance, starting at the node, you grow exponentially. Otherwise, you would not get small diameter. And so the logarithmic diameter of the whole networks as a function of the whole population. Because with real extended things, you would get polynomial, and you would, yeah, and it would be large distances, right? So I think this is still reasonable. There is certainly also modifications by regional things, and the regional things are coupled a little bit, and this have some inhomogeneities. But actually also you can extend it. I mean, we are working at the moment extending this BGR to some regional stuff. Not lattices, because lattices are not part of this BGR theory. So the classical percolation theory is not, because it's not tree-like. But still what you can do, take large cities with relatively large, but small compared to the whole population, where you can saturation of, say, an epidemics have locally, that happens in a village or a town, before actually the epidemics is at the far end of the country or really gets big over there. And this thing still has in 2 dimensions, the phase transition is still captured by the theory I presented here essentially, right? In the directed version. But there's no, the timing is different. This results on the timing, on this universal shape of the epidemic curve. This is not longer true here, because you have a more stretched thing, right? So this needs here really this logarithmic diameters. And so there are certainly a lot of extensions you can do. The math numerically also we do with the Frankfurt people to see a little bit this lockdown, regional lockdowns, how this really impacted, but we work essentially also with BGR, branching process theory, in this setting.
Thank you. Thank you for a very nice talk and a great discussion session. I think we're out of time now, but and again, thank you for visiting us here. Look forward to future interactions. So bye everyone. Thanks for joining. See you next time.